there is something called supercontinuum. It is like this. Suppose I send a high power laser of nanosecond pulse width. I send through some sample of, for example, some sample of ethyl alcohol or acetone. If I focus it, I will get this. This is lambda. We put omega L. So you will have omega L plus or minus omega Raman. Now you put N. For example, instead of ethyl alcohol, with ethyl alcohol you get only 1. N is only 1. With CO2 gas, which I had shown you, N can be, in fact N is 9. This is what we have observed here. That means, look at it, you will have lines like this. You understand?
Yes, yes.
Now
This is
look at it.
ordinary Raman.
Ordinary Raman, stimulated Raman.
Stimulate.
Not ordinary Raman, this is the Raman laser.
Raman.
You get so many lines. These are the lines which are the vibration features. Plus, if you look at carefully, this particular molecule can have vibrational frequency plus rotational frequency. CO2 has vibrational frequency for which this omega r will be 1000 centimeter inverse. But this molecule can rotate. How it can rotate? Look at this one. I take the example.
Symmetry, what symmetry?
No, can you take that?
Yes.
Yes. No, this okay. Now look at it. A CO2 has something like this one. Yes. Molecular structure. Imagine this is C, this is O, this is O. Then look at this one. This is vibration. This is vibration. In addition to this, the molecule can rotate. Okay? Not only to rotate like this, the molecule can rotate. So it has 3 rotational degrees of freedom. So I would say it can rotate along x-axis, rotate along y-axis, it can rotate along z-axis. When it rotates, we always speak in terms of moment of inertia. IA, or I put IX, IY, IZ. You know what's moment of inertia? R square.
Yes.
MA square, or whatever it is. It is a moment of inertia in principle in physics. This means it's the resistance of any object against rotation. See, this one, unless I push it, it will not move. This is called inertia in the linear direction. If I don't twist like this, this will not rotate. This is called inertia against rotation. This you measured in terms of moment of inertia. Okay. Since you have 3 degrees of freedom, in fact, for a plain molecule, you have only 2. See, or a planar molecule, it cannot rotate like this. It can rotate like this, it can rotate like this. You understand? It can rotate like this. Okay? If you say this is y-axis, I, y is not equal to 0. It is rotating like this. It can rotate like this and this, but it cannot rotate in this direction. It will be rolling. Rolling is not rotation. It cannot rotate in this direction because it's a linear molecule. So it has 2 degrees of freedom. Next step. We have been able to quantize vibrational energy. Same way you can quantize rotational energy. When you quantize rotational energy, the jump from one rotational level to another rotational level will be absorption. The jump from one rotational level to another rotational level will give you light or electromagnetic wave of longer wavelength or a smaller frequency. Longer wavelength or smaller frequency. The frequency associated with the Raman rotation, look, this is Raman vibration. Raman rotation will be about 10 centimeter inverse. Now look at this one. You can imagine this laser, YAG laser, 532. The wave number for my YAG laser, 532, is 18,750 wave number. Am I right?
Yes.
You can check. You find out the reciprocal of 530 nanometer. You have a calculator?
He has one.
Yeah.
Yes, 18796.
796.
96.
Okay. 796. Okay. Now look at it. I am using this. Send it through my CO2. I get a laser. Look at it. 18796. This will be 18. This is 1000. So this will be 17796. Like that, I will have so many, right?
Yes.
This will be 19796, right?
Yes.
This much is clear. Next step. These are the vibration frequencies. Now, if I have 10, I will have like this. Understand? I will have so many transitions. All of them will be lacing. Then I have so many of them starting from this end to this end, you get quite late. Understand? Let me explain.
But last time we talked about discrete tunable and continuous tunable.
Okay.
So if this for CO2 laser or for these molecules, we can't get discrete.
This is, you will get discrete, okay? This is, in reality, it is discrete.
But
But it is so crowded, the frequency is so crowded.
so we eliminate this.
No. Try to understand. You will get so many number of frequencies. What you will get from here will be like this. Understand?
So it doesn't affect the whole frequency. This small thing, 10 centimeter, does have a real effect in.
That's what I'm saying. That means if I look at vibrational transition alone from CO2 molecule,
We'll
okay,
get discrete.
you will get discrete.
That's correct.
If you look at the rotational and vibration together, you will get again discrete, but it will be too much crowded,
Close to.
very close,
So it's also discrete, but very close.
very close.
Ah.
Next, what do you do? Next, what do you do? Instead, this is for CO2, which is a simple molecule. I take a very complex molecule. I take a complex molecule like hydrogen peroxide, hydrogen H2O2, hydrogen peroxide, or fibers. What is it? 1 minute. This is called the erbium doped fiber, quartz fiber or a glass fiber. Glass fiber, you can add erbium, you can add so many things. It is like you take a cake, you can add a little sugar or a little salt. Just leave it to your own fast taste. Once I have, then look at it. You imagine this is a fiber. What I will get is this will be 400 to 800 nanometer. When I get something from 400 to 800 nanometer, it becomes a white light. Now I have got a white light laser.
Continue.
Okay?
The same CO2 we can get white light.
What is it?
For CO2 we can get white
You
light.
cannot. CO2 you will get many colors, but you can see all the colors.
But crowd.
Not even crowd. You will see many of them. But still you will see blue, green. If you choose some type of fiber which are specially prepared, and if you do the same YAG laser, you will get a pattern which is very close to white. In fact, if you look at it, you cannot see the difference between pure white light and this white light. It is so crowded. It is something like you're taking a photograph on a Friday evening, but you will see only the heads. You will never see the human beings, right?
Yes.
If you look at a height,
Yes.
you will see a crowd of people going, not the individual. This is what is called super continuum. You see, it is a continuum, means it is a discrete, but it's so close, it looks like a continuum. Next point, why you call it super continuum? Is it a laser? First question. Is it a laser?
Yes.
It's not a laser. I tell you what. A laser means it should have pure wave,
Coherent.
coherent. It is totally incoherent because it has so many wavelength. So, for a super continuum, coherence bad. Very bad. Understand?
The condition for a laser not here.
What is it?
The condition for laser is not here.
Yes. The quality of a good laser is totally absent. Quality of good laser is totally absent because it is continuum. First thing. Since it is a continuum, there is no question of phase correlation and all that. It is very bad. Next step. Why at all you are interested in this one? But look at this one. This will come through a small angle of 1 milliradian, because if you look at Raman laser, which I will show you, the Raman laser will be a very good laser, spectrally very pure, and it has an excellent coherence. And the YAG laser has 1 milliradians divergence, right?
Yes. For NDIAGs.
In YAG laser.
Yes.
When I put through some liquid, I will get a Raman laser at 630 nanometer. This also will have 1 milliradian. What I have got now is a new type of laser, which is spectrally pure,
Coherent.
which is temporally pure, and it is very collimated coherent. So it is temporally and spectrally coherent. Understand?
Okay.
This Raman.
Raman is very coherent.
But super.
Wait, this is very good. But here, there are so many wavelengths, so many frequencies, so it becomes white, but only advantage is the same kind of light is produced in this direction, so it is spatially coherent. Spatially narrow. I would not even say very narrow.
Because it is.
It will go in a straight line, like any other laser.
So if it is especially narrow and it's a new wavelength, why it's not laser?
No, laser means, first thing, all that we have seen in this semester are not lasers. Wait a minute, you should understand. A neodymium laser is a very good laser. But when it produces second harmonic generation, in the medium there is no population inversion, the crystal.
Yes, that's
It is just converting the frequency.
Yes.
Understand?
yes.
Same way, all these are frequency converters. Only difference here is, this is making use of the property of vibrational and rotational frequencies of Raman medium getting converted to laser.
No loss in energy.
Huh?
The energy will not loss.
No, energy will be lost. Because when you put some energy, you will lose some 30% of the energy, 40% of the energy.
Or
as
scattering
heat.
for heat.
Super, but the
Wait.
powerful super.
It is not the power which is important. Power will be less. This is true. If I start with 100 millijoule, what I get here will be only 2 millijoule. 98 millijoule will be waste.
This for super.
Yeah, super. But the advantage, you get a white light which is collimated, which goes like a bullet. All other light will diverge out. You know lighthouse? What is this? Sea. You know what is a sea, right? You have a ship.
Okay.
In the harbor, there will be a tall tower. And in the tower, there will be a light coming out like this. This is called lighthouse. What is it in Arabic?
Manara.
برج منارة.
Manara.
Manara?
Noor. This is light. It's noor.
It
You
will
can
be,
see that light from far.
yes.
It's like
See, when the light comes
pulse.
out.
It's like pulse.
Yeah, it will be always pulse. It's not pulse, it will rotate.
Rotate.
Then people at some 30 kilometers can see
Yeah.
that there is a place, there is a lighthouse, so we can go. Otherwise, in the sea, it's very difficult where to go.
Yeah.
Understand? So this is the one which gates. Now, what is important is you produce new type of lenses, mirrors, everything, so that light goes like this. Understand? This is a white light done with lens arrangement, so it goes a long distance. Now, in the supercontinuum, you have produced a light of very narrow, like this. It will go for many kilometers, not 10 kilometers. It will go for hundreds of kilometers.
From this one. So
Yes. Because it's only 1 milliradian. It's like any other laser. It is not a pure laser, but collimated. It goes to a long distance.
And there's application for this?
That's application. We will come to see the application. You see this one? So,
They use Raman in this one, or LED or another source.
for what? For what?
Lighthouse source.
Lighthouse? No, they don't use
Light,
laser.
light,
It's
light.
just they use a lens. Lens or a mirror. No laser at all. Because lighthouse is there even in the days of Greeks and Romans. Now let me put all this together. To do this, what you must have a picosecond or femtosecond laser pulse. Which is available from NDI. Remember, you cannot produce supercontinue in many. You have only limited. NDI, Sapphire, Ruby. That's it.
These three only.
Only 4 lasers will produce picosecond, femtosecond lasers. Of course, dye laser. India, Sapphire, Ruby, argon ion dye laser. Out of this, always the best is this. It's a workhorse. You know what's called workhorse? What's a workhorse? No, it will be working and working all the time.
All like
You
a
can
horse.
kick it, you can kill it, but it still work. On the other hand, this argon ion is a touchy laser. This one, if you, after 5 years, it will say, no, I am tired, I will go to sleep. This is what it does.
The gas will go away.
Yeah, gas will leak out. Okay, this is a neodymium laser. You can send through fibers. 1 second. You can send through H2O2. This is peroxide. 3. You can use D2O. These are the few materials. Then you get picosecond or a femtosecond supercontinuum. Just remember this one. You will get picosecond pulses. You can get
From 400 until 700?
picosecond pulses. Imagine, forget this one. Suppose I send 50 picosecond pulses. We are trying to generate in our lab. Once it is ready, I will show you.
Is it difficult?
You should have enough energy.
This is very warm, all these labs.
Very bad.
Not
There is no air circulation.
Yes.
Okay. So these are the media. This is the laser.
this is
This
output.
is what you will get, output. Okay. What is happening inside is mostly SRS, stimulate Raman scattering, stimulated Brillouin scattering. stimulated Raman scattering, stimulated Brillouin scattering. I told you what is a Brillouin scattering. Maybe if you wish I can explain what is this one. SVS means stimulated Brillouin scattering. Brillouin scattering means, look at it, I send, the whole medium will have certain vibration. It is something like, look at this one. It is vibrating. Okay. It is not the molecule. It is the lattice. You know what's the lattice?
It's the crystal.
Huh? Lattice crystal. The base of the crystal is called a lattice. So when I shine with the laser, the whole lattice will start vibrating. Not the ion, not the molecule. The whole lattice will vibrate like this. This vibration becomes something like a rotational frequency or vibration frequency. So you will get laser with this kind of frequency modulated. The frequency shift for this will be, look at it. Look at it. Put this word. This will be 1 centimeter inverse. Here you must remember this one. Omega of laser is 18796. Omega of Raman vibration is 1000. Omega of Raman rotation 10. Omega of Brillouin, this Brillouin is only 1 centimeter. Since all of them take place simultaneously, plus there is something called self-phase modulation. Self-phase modulation. That will produce another small shift in the frequency, but it's not very important. Don't bother about it. It is more of mathematical, which you cannot really see this one, so I don't want to go into the detail. All these put together leads to white light. Since it has a narrow collimation, this is called super continuum. Continuum. Next question, I have produced. What is the use of this one? What is the use? I can tell you what is the application of this one. Firstly, you must know what is absorption spectra. Then only you will understand the application of this one. Your friend Zweil has used this one, supercontinuum, for his PhD, and no, not for his Nobel Prize. I will explain how he got that one. First, you must know what is an absorption spectra. It's like this. I start with xenon lamp, which will give light from 200 to 800 nanometer. It will produce light everywhere. Then I put a lens, allow it to fall here. Put a grating, then the grating will spread out the light like this. Then what I do, I block everything. I block everything. I allow only this light to come. This light alone to come here. Remember, I have blocked it. It is coming through a small slit. I put a mirror. This mirror has 50% reflection. That means 50% of the light will be reflected, another 50% will go. I put 100% mirror. This will go. Here, I put, for example, all this experiment I can show you later. You have done this experiment. You must have done in 532 or 531. You did 631 or you did some
We
experiment.
study it with you, theoretically in spectroscopy only.
But did you do any experiment? You had a course in experiment.
Yes, but we don't take this one.
No, quantum optics.
We will take it after next semester.
No.
Master.
Master, you had one course. 531 or 532 or something like that.
We worked in laser diode characterization or characterization,
Laser diode. Then what did you do?
the absorption.
That's what I'm saying.
But for one die, for 32
Whatever it is, give some name. Okay.
absorption, yes.
You did absorption spectrum.
Yes.
That's what I'm telling.
But about Zoel, no.
We will come to that later. We will come to Zoe later. You are still in the beginning.
This is for the absorption spectra.
Regular normal absorption spectrum. Okay, then this is, let me put, this is alcohol or acetone, very simple. And then I have another cuvette in which I have acetone plus your dye, some dye. Then what I do, let me say 50 photons go here, 50 photons go here. What comes out here will be 40 photons because there will be reflection, so many things, you will lose a lot of light. What comes out here will be only 20 photons because the dye will absorb the 20 photons. You understand?
Yes.
Then what I do, look at it, log to the base 10, I naught over I. This is defined as absorbance. How much will be that? You can easily see log 10. I naught is 40, I is 20. So this will be log 10 to the base 2.